In today's video, we're going to look at permutations with identical elements. And we do this because you often deal with permutations where there's identical items and they affect the overall permutations or arrangements. So, I know today was a snow day and I've been hoping to do an activity. You're going to form groups of 3 people. Instead, through this video, here's what you'll do. I'd like you to take the time to go through these steps. First and foremost, be sure you take the time to do this or you're going to jeopardize your learning, if you will. It's just not going to be any value if you just go ahead in the video. I'd like you to try these out. So in step 2 here, try and figure out all the ways you can write the word dole. Like, write them out. How many are there? Ask yourself, how many unique combinations are there? After that, try it with the word doll. Notice the difference. How many unique combinations do you think that has? After that, move on to the final one here and try the word lol, or LOL with another L. And how many unique combinations of that do you think you have? Hopefully, once you go through this, you'll sort of see a general rule for finding the number of permutations or arrangements when some items are repeated. So go ahead and try this activity. So pause the video and come back when you're ready. Okay, hopefully you've taken the time to do this. Let's take a look. So if you look at the word dole, how many permutations did you find? Here's what I got. So as you can see here, they're all written out. If you count them up, there's 24 of them. Each one of these is unique. None of them repeat. So if you had to spell the word dole, there's 4 spots. So you have your 4 stage lines, and you get to choose. So at first, you get to choose from 4 letters. And after you've chosen one, you're down to 3. And this just continues until you're out of choices. And we know that for separate stages, stage 1 and 2 and 3 and 4, you multiply. And you end up with 24. So again, those choices, in your first choice, you could choose a D, O, L, or E, 4 of them. Once you pick one, your next choice, you're down to 3 letters. And then so forth, you're down to 2 letters and 1. So to answer question 3 from the start, you can see each arrangement of dole is unique, and there's 24 in total. Let's take a look at this now using permutation notation, which we looked at in last class. Here are the arrangements. There were 24 of them. And they're all unique. So we had used this notation where P meant permutation, and you were able to choose from 4 ways, 4 letters, and no restrictions, so 4 choices. That was 4 factorial. We said for permutations of n items, we make our choices, and the formula is n factorial divided by n minus r, then you take its factorial. So in this case, we have n items where n is 4 for the letters, and we can do it our ways. So there's 4 choices. If you work that out, you get the following. Permutation of 4 choices across 4 items, and you substitute, you end up with 4 factorial over 0 factorial. And you said 0 factorial is just 1, and you end up with 4 factorial, and that gives 24. Moving on, in part 4 of the activity, you look at the word doll. So how many arrangements did you get? Well, I used a system where for one L was just L, and then the other L used L1, so I could keep track. If you look here, you can see there's a bit of a difference. Notice there's 12 black and 12 red. That's because there's some duplicates. What we can say here is, of the 24 arrangements listed, well, there's only 12 actually different from each other. And this is because there's two L's that are identical. As you can see, what that means is these two L's can trade places. You could have L1 beside L, or you could have L beside L1. So there's 2 factorial ways to do that. So for this, we say that the number of different arrangements is still our 4 factorial, but we have to divide it by the 2 factorial because of the 2 repeating L's. So you get 24 over 2, that's 12 ways. So let's jump ahead and look at a general rule already for this. So in other words, to find the number of permutations, you would divide the total number of arrangements, here we had 4 factorial, by the number of ways in which you can arrange the identical letters. And we had identical L's, and there were 2 of them, that's why we divided by 2 factorial. If you want to generalize this, you can imagine n distinct items where you have repetitions. And what kind of repetitions do you have? Well, you could have A, one kind, B is another kind. And for each of those kinds, you take their factorial. So it's n factorial divided by A factorial times B factorial times however many identical items, or maybe letters, there are. So in full summary, there's your formula for permutations when there's n distinct items. However, there turns out to be A identical items as well, B identical items, or maybe some other number, maybe C, D, E, just depends how many identical items there are. That's why I use the dot, dot, dot. In the last part of your activity, you were asked to look at LOLL and see how many arrangements there were. How many did you get? Here's my list. That's interesting. I see 24 in total. And how many of them are unique? Actually, as shown in black, there's only 4 unique permutations. And this is using a key of L2, L1, and L, because L is repeated 3 times. It's duplicated 3 times. So since it's repeated 3 times, it can be in 3 factorial or 6 positions. You have 3 L's, so you get a choice of 3, you pick one. Then you get a choice of 2, and then you get a choice of 1. So 3 times 2 times 1, 3 factorial, 6 positions. So, with permutations with identical elements, for this case, let's take a look at how it works out. Remember, we have n factorial over A factorial times B factorial, dot, dot, dot. And for our specific example, it looks like this. LOLL is 4 letters, so there's 4 ways to arrange those letters. And then the only repeating element is the 3 L's, so you have to divide by 3 factorial. Okay, it's like A equals 3, and there's no B, there's no other repeating items, it's just the L's. So you do 4 factorial over 3 factorial, and you use your calculator to evaluate that, or you can just use your mind, and you'll get 4. So we say there's 4 ways to arrange LOLL. Moving on, let's do some examples so we can really demonstrate this new formula with when you have several items, so n items, and there's identical elements. So in how many ways can you arrange the letters of the word Toronto? Okay, and more specifically, you want to make distinct words. The first thing, I count 7 letters. 1, 2, 3, 4, 5, 6, 7. So you're going to say that you have 7 choices. With these 7 choices, it's like your n equals 7. Then look at the letters, and which ones repeat? I see an O here, an O here, an O here, so there's 3 O's, and then I see a T and a T, there's 2 T's. None of the other letters repeat. So this is what we say. We say with 7 letters, 7 factorial, there's 2 of them that repeat, your T's, and 3 that also repeat, your O's. You use our general formula for permutations with identical elements, and it's 7 factorial divided by 2 factorial times 3 factorial. And when you evaluate that, you get 420. So there's 420 ways to make distinct words. All right, how about now? Now, in how many ways can you actually arrange all the letters of the word Toronto? They have to begin with a T. So give some thought to that. So in your word Toronto, it has to begin with a T. And I see here there's 1, 2 T's. So the first letter I'm going to use with my stage lines here for Toronto, it's going to be restricted. And the restriction reads like this. You get to choose from 2 T's. And that means there's 2 choices for T. After you've made this choice, there's no other restrictions, so you can just choose from the remaining 6 letters. So all the other stage choices here, you choose from all the remaining 6 letters, one at a time. Each time the choice goes down by 1. So when we choose here, we have 6 to choose, then we have 5, 4, you get the idea, 3, 2, and 1. Now we've taken care of the first part in determining all the arrangements that begin with a T, but we have to remember to divide out by identical items. So the word hasn't changed, it's still Toronto. There are 2 T's, 3 O's. So this is how you resolve one of these questions. Your numerator is our 2 times 6 factorial, right here. You still have to divide out by the 2 T's, so 2 factorial, and the 3 O's, 3 factorial. And when you resolve that, when you simplify that, throwing that in your calculator, which would be recommended, you'll get 420. Okay, part C now. How many ways can you arrange all letters of the word Toronto? It's got to end with a T. So it's the same kind of approach. There is a restriction. It has to end with a T. So I've got my stage letters, and I need to spell Toronto out with 7 stages. So the last stage has got to end with a T, and then I look back at Toronto, and remember there's 2 T's. This spot here, I can choose from 2 T's. And in fact, after doing that, there are no other restrictions. And it's quite clear that for all the other choices, wherever you start, you get to choose from 6 remaining letters now. Okay, so it doesn't really matter where you place them. Usually we go in order. Let's see what we have here. Okay, so 6 choices, 5 choices, 4, 3, 2, 1. And it's very similar to the last example. You have all your choices here. 2 times 6 factorial. But you need to remember, you got to divide out by the common identical elements. And the identical elements are T, there are 2 of them, O, there are 3 of those. So we come down here, and we remember to divide out by 2 the T's, and 3 the O's, of course, using the factorials of those, and you get 420 again. Pretty neat stuff. Okay, let's try some more examples to continue building on this new skill here of identifying the arrangements for n-to-6 items with repeated identical elements. So example 3, how many different 7-digit telephone numbers contain 3 5s, 2 2s, and 2 1s? Alright, well here's the numbers they're letting us use. Okay, so we can arrange these how many ways? So here's a phone number per se. Okay, so I count 1, 2, 3, 4, 5, 6, 7 different digits as it was given in the problem. Here's 7 digits, and I need to arrange them. So I'm going to need my choice lines, and they're below here. First off, I can immediately, right away, pick from 7. So I could pick this one first. Then I can pick from 6. Now I can pick from 5. And so forth. I can pick from 4, 3, 2, and 1. So it's no different. It's still our usual 7 times 6 times 5 times 4, 3, 2, 1. 7 factorial choices, okay? The difference being there's identical elements. There's 3 5s, 2 2s, and 2 1s. We have to divide those. We have to divide those out factorially, and it looks like this. So you still have your 7 factorial, because there's 7 digits in the telephone number, 7 choices, but because of the repeating elements, the repeating 5s, the repeating 2s and 1s, you do have to divide those out. So there's 3 5s, you divide by 3 factorial, 2 2s and 2 1s, that's why it's 2 factorial and 2 factorial. You simplify that and you get 120 ways to achieve this type of phone number. Alright, last example here, and it's got a few parts, so here we go. How many different words can you make using all the letters of MI, SSI, SSI, PPI, Mississippi? But if, first off, there's no restrictions. First thing you do is you have to identify how many letters you're actually dealing with. So I have them here. Let's take a look. You count them out. How many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. There are 11 letters. So I right away have 11 choices. So with these 11 choices, here's one hypothetical word. I choose to place a P. I chose from 11. I choose a P again. I chose from 10. And you just continue this. You can see the choices that remain as I go along. So now I have 5 choices left. 4. And until we get to the end. So there's one option. Pissy Misses. Which is definitely not a real world. With those 11 choices at each stage, I had 11, then I had 10, then 9, all the way down to 1. You first write out that there are 11 factorial choices. Your next steps to identify the identical elements. So let's do that. I've got 2 P's. Let's do the S's here. I've got S here, S there, there's 4. Okay, so I've got 2 identical P's, 4 identical S's, 4 identical I's. Given these duplicate letters, we have to divide them out as follows. We have 11 factorial for the 11 letters and choices for MSI, SSI, PPI, Mississippi. And we have to divide as follows. So the 4 factorial for, say, the 4 S's, another 4 factorial for the 4 I's, 2 factorial for the 2 P's. We simplify and we find that we have 34,650 different arrangements. For part B now, using the word Mississippi, what if the word has to end with an I? What do you think we have to do for that? Well, again, we need our stages, and there are 11 of them because there's 11 letters in Mississippi, so we'll get these 11 choices. Now, there is a restriction. It has to end with an I. Well, there's 4 I's. So on the last letter, we'll get our 4 choices. Okay, we can choose from the 4 I's. So here we will get 4. Now, after we've made that one choice, whatever it may be, whichever I it is, we're left to filling in the rest of these spots, and there's 10 letters to choose from. Okay, only one of the I's will end up here, so there's still 10 choices in the next spot, and as usual we start on the left, so there's 10 here, and then there'd be 9, etc., 8, all the way down to that 4 we first did. So we say there's 10 factorial times 4. 10 factorial times 4. And because there's still the duplicated P's, S's, and I's, we have to divide them. we divide them using their factorial amounts. So 2 factorial for the p's, 4 factorial for the s's, and 4 factorial for the I, and it looks like that. Excuse me. 2 factorial for the p's, right here. 4 factorial for the s's, we'll say this 4. 4 factorial for the i's, that 4. Divide out those repetitions. You simplify and you get 12,600. Okay, part C, still using Mississippi, asks, how many arrangements now if the word cannot end in an I? Well, this is where you have to kind of realize the way things are worded clues you that you need to use the indirect way. So let's do that. Because we just did all possible restrictions, then in part B we did must end with an I. This here, the word cannot end in an I, is the complete opposite of part B. We discovered last class that for the indirect method, or the indirect way, we use the following. Now here's how it applies for our question. So the permutations that cannot end in an I, which is part C, is equal to the total permutations minus the opposite of ending in I, which is it can end in I. So really, we take our answer from part A, the total permutations, and subtract our answer from part B, where it does end with an I, and you end up with all the permutations where it cannot end in an I. So from part A, we learned that the total permutations of Mississippi's letters is 34,650, and in part B, we found that if it does end in an I, it's 12,600. When you subtract those two, you end up getting what part C requires. It cannot end in an I, and that answer is 22,050 ways. All right, just to recap. So as we said earlier, if you want to find the number of permutations, when there's identical elements, you divide the total number of arrangements by the number of ways in which you can arrange the identical letters. So for n items, it's n factorial. When there's a, b, etc. identical items, you divide by a factorial times b factorial times whatever amount of identical items, each of them factorial. Not that bad, right? All right, to really solidify your understanding, here's the homework. It's a handout. It's actually a handout from your textbook or workbook you're going to get. Anyhow, it's page 64, 65, number 1 to 3 and 6. You can access that on our website, and I'm showing you here what it looks like. There's the website, and when you go down to today's date, Friday, February 8th, there's the actual file you'll download, the handout, and there's solutions for that. Give those a try, bring your questions to class, and we can take those up when we're back. If you're really stuck and burning for the right approach or answer, send me an email and I will get back to you. Thanks and good luck.